everybody, and welcome to the 68th session of the Porous Media Tea Time Talks. I'm very excited today to welcome two excellent speakers, and we're going to be starting with our first speaker, Callas. Catherine is a PhD student at Stanford University in Sally Benson's group, and she's been using machine learning to predict the movement of CO2 in the subsurface. So we're going to dive straight into Catherine's talk, but before we do, just a comment to say that you can type any questions that you may have to Catherine, and we can read them out at the end of her presentation. So feel free to type out any comments that you have whilst her talk is ongoing. And with that, I'm going to hand over to you, Catherine.
Great. Thanks, Catherine. Can you see my screen okay?
Yeah, it looks great. Thank you.
So hi, I'm Catherine Callas, and today I'll be talking about how we can enhance carbon storage assessments through the use of probable simulation. So to develop safe carbon storage projects, we need to be able to accurately model the subsurface and represent the geology accurately in order to avoid potential risks. And we can use this geomodel in our numerical simulations to understand how the plume will migrate and the pressure will evolve when we inject CO2 underground. However, a lot of the locations that we're looking at for carbon storage projects have limited data available, particularly those in prospective saline storage reservoirs. So we may only have one or two wells that have been drilled with data, and this can lead to a lot of geological uncertainty. And as we drill more wells, we can gain more certainty. However, we need to be able to capture this uncertainty in our numerical simulations to understand kind of the array of things that might happen when we start injecting at the site. And this uncertainty can end up leading to significant variations in our numerical modeling results. So the top two figures show permeability maps that are 2D, and they have the same permeability at the well that they're conditioned to, which is on the left-hand side, and the same correlation lengths. The only difference between these two permeability maps is the random seed that was used to generate them. But as you can see, the corresponding gas saturation output after we've done numerical simulation have pretty different results. So on the left-hand side, we would estimate the radius of the plume to be about 2 kilometers, while on the right-hand side, it's about 3.2 kilometers. And the area that we would need to monitor, get permitting for, acquire the land rights for, is over twice as large on the right-hand side. And so in order for us to capture this uncertainty, we would need to run hundreds of numerical simulations, which can be quite expensive with traditional commercially available numerical simulators. So one way that we can try to address this issue is using a general purpose AI-based reservoir simulator, such as the one that was developed by Gogo Wen at Stanford called CCSnet.ai. So CCSnet.ai can provide instant, full physics, multi-phase flow simulation predictions with high resolution and comparable accuracy to numerical simulation. And so the way that we do this is first we have our inputs, so our geomodels, the reservoir conditions, rock properties, and injection plans. And we'll sample the domain spaces for each of these inputs and run numerical simulations using a commercially available numerical simulator and get our corresponding outputs, so our pressure distribution, our CO2 gas saturation. Then we can use these input-output pairs to train a machine learning model that can now infer in this domain space in just seconds. So here is a screen grab of the ccsnet.ai webpage, and we're looking at a 2D isotropic radially symmetric reservoir. The top is the permeability map, and on the bottom, we have our corresponding gas saturation. And in this red box, we're just changing the random seed for the synthetic field. So we're not changing anything else. And as you can see, as we change it, we start getting large variations in our CO2 gas saturation. Another thing to note here is it takes just a couple of seconds, so feel free to go on this webpage and play around. But we can get really fast results, which can help us capture this uncertainty in a reasonable amount of time. So one place that we've applied this workflow is at the Otway International Test Center. So the Otway International Test Center is in Victoria, Australia, and we have multiple wells that have been drilled over the years as they've done a range of experiments at this site. For our particular experiment, we're injecting about 10,000 tons of CO2 into one well, the CRC3 well, and we've drilled 100 meters up dip, a monitoring well. We've chosen to drill in a very heterogeneous part of the reservoir in the Parade Formation, which is characterized by small-scale heterogeneity. It's a delta front depositional environment, and we have a lot of data at both the wells. So we have well logs, we have mini perms, special core analysis, routine core analysis, in addition to continuous core at both wells. However, there's still a lot of uncertainty, even in just the 100-meter difference between the injection well and the monitoring well. On the right-hand side, you can see the geomodel that's been developed by the team at University of Melbourne. And just the red portion is where we'll be performing our numerical simulation studies. And this red portion has about 5 million active grid cells that are super fine resolution, so 3 meters by 3 meters by 0.3 meters. And we'll be doing numerical simulations in Eclipse in order to generate our training data set. And so the reason that this site was a good place to test our methodology on is that we want to keep this super fine resolution in our grid cell size, as well as a very fine temporal resolution. So we want to be getting data about every single day to be able to match with our pulse neutron logging that we're getting at our monitoring well. But we also have full physics. We want to have all the multi-scale heterogeneity as well as multi-scale problem, and it can be very computationally expensive to run these numerical simulations. So on average in Eclipse, it took anywhere from 2.5 days to about 5 days for these simulations to run. So we wanted a faster alternative that could help with project decision-making, but still have all this full physics and the fine temporal and resolution. So to generate our training data set, we ran 500 numerical simulations in Eclipse E300 with this super fine grid size cell. And we varied the horizontal, the vertical permeability, as well as the porosity and the rock type. And we generated composite rock directional relative permeability curves and imbibition curves using Land's trapping model, and also had composite rock capillary pressure curves and capillary pressure heterogeneity. And we injected 150 tons per day over 67 days and then monitored 60 days post-injection. And we chose a 3D UFNO model for our machine learning model. So this is a UNet as well as a Fourier neural operator model. And in the pre-injected period, we just did a single step time, and we were looking exclusively at the gas saturation. So in order to judge how good or bad our model was doing, we looked at the L2 loss. And so we were able to achieve a training relative error of about 3% and a test relative error of about 6%, which was suitable for our pre-injection needs. So the model resulted in about 80,000 times average speed up and runtime. So our Eclipse runs were parallelized on 30 CPU on one machine, and on average took about 2.5 days to 3 days to run. In comparison, our model can infer our predictions in about 2.6 seconds. So that's a huge speed up and can really aid if we want to look at things like different injection rates in our decision making. So one thing we cared a lot about in the pre-injection period was the breakthrough time at CRC8. So the figure here shows the probability of CO2 being present. So the dark red shows that there's an over 95% probability that CO2 will be present at that grid cell, and the blue is a less than 5% probability CO2 will be there. And as we can see, the CO2 is moving in 3 major layers, a top, middle, and bottom layer, with the middle layer being the fastest. And the 2 red lines are our injection well and then our monitoring well. So we were able to see that by day 23, our middle layer would have over 80% probability that it will have reached our monitoring well. And this was great for our pre-injection talks with stakeholders for the project. So it helped us gain confidence that our experimental timeline and monitoring plan would be suitable to catch breakthrough. And we were also able to see kind of estimated times of breakthrough in the other 2 layers. We also looked at this in a 3D view. So this is the cross-section of the plume as it evolves over time. And we can see, again, this probabilistic gas saturation map as it evolves over the progression of the 23 days. And lastly, another thing we really cared about for this project was looking at what we would see at CRC8, our monitoring well. So the left-hand side shows that probabilistic gas saturation over time, and the right-hand side is the average predicted gas saturation. So we were able to see that that middle layer around 1440 meters had over 80% probability that it would have a gas saturation about 25% by day 25. So for future work, we're working on expanding our training data set, as well as extending the model for the full injection time and creating a model for the post-injection period to help with history matching. So thank you for listening.
Thank you, Catherine, for that really good presentation. If any members of our audience wish to ask any questions, now is the time to type them up. And I will just start just so we can give our audience some time to type things up. But do you think that we can get an accurate prediction of the CO2 plume movement just through saturation, or are you planning to incorporate things like pressure and other things like that in your future work?
Yeah, great question, Catherine. So we can also generate a model that will help with the pressure prediction, and you can couple these two if you wanted to in order to get accurate predictions. So we'll be investigating a saturation-only model as well as potentially a combined pressure and saturation model and see how that impacts our results when we do our history matching.
Great, thank you. Sang, do you have a question?
Yes, I do. So you mentioned about your site having small scale heterogeneity, which could be an ideal case for you to test your model. But what kind of length scale of heterogeneity are you working with?
Yeah, so I would say this site has very small scale. So like I did core experiments with Catherine Spurin at this site, and we saw lots of heterogeneity just within one single core. And so capturing that in a grid cell, even though we have a very fine grid cell for numerical simulation, 3 meters by 3 meters by 0.3, still feels quite large for this site. And so that's been a challenge, is how to capture the small scale heterogeneity in a grid cell that size, and what features will be important. And so that's something also that I'm playing around with by changing the composite relative permeability curves, as well as the anisotropy in the model. And so that way we can see what factors capture those heterogeneities the best when we do our history matching.
Okay,
Great, thank you. I'm going to read out a question from the audience. So thank you, Hattie, for your question. Would you please let me know how you have included the lithology in the simulation?
Yeah, so the team at University of Melbourne generated the geomodel initially. So they looked at the different lithologies. So they had a couple different main facies that they used to generate the realization. So carbonate cement, a proximal mouth bar, as well as a distributary channel. And they used seismic to generate these. And then within each facies, they then populated the rock types as well as permeability and porosity, and generated those, I think, doing geostatistics. But I think there's a paper that I can refer you to with like the full workflow if you're interested.
Great. Well, thank you so much. And thank you so much for your presentation, Catherine. So I'm going to hand over to Sang now, who is going to introduce our second speaker.
Okay, our second speaker today is Daniel Lizama. I'm going to introduce him to all of you. So Daniel is a PhD candidate at the University of Puerto Rico, and he's also a student intern at Sandia National Lab in the Department of Geomechanics Research and Application. His research focuses in efficient machine learning applications for multiple physiological environments with limited data sets, including geological phenomena and brain-computer interfaces. In today's talk, he will be talking about machine learning-based microseismic event detection. Daniel, floor is yours.
Can I share screen?
We can see it, Daniel.
No, that's you present. Okay. Are you seeing my screen or?
Yes, we can see your screen.
Okay. Let me put here. All right, so yeah, we're here. I'm going to talk about microseismic learning-based, machine learning-based microseismic event detection. So this is a little more towards data-driven type of. Oh, hold on, you're on the wrong swap percent. Okay, there you go. Okay. So let's see. So first we're gonna go over the motivation would be and the specifics on the projects and the Illinois Basin Indicative Project where we are applying this machine learning method. So firstly, here we are talking about injection of CO2 to the surface, where obviously you inject the CO2 onto the subsurface, and then the pores get saturated and start increased pressure, and then you get, once the pressures increase, you get more. The fractures start to happen. So they could be happening on new fractures, or I can induce new fractures, and they could happen on old fractures that are already in the subsurface. So then, to attack these types of scenarios and learn more about the conditions, we apply machine learning methods to analyze nonlinearities in the mapping between the inputs and the outputs. So here, machine learning has been for a long time successfully applied to machine learning data, and for microseismic and seismic events. And then these are our goals, which is, in our case, to apply machine learning techniques for seismic wave data analysis and event detection at the Illinois Basin Indicative Project. I'll talk that in a bit. And then here specifically, we're only talking about the detection part of this stuff. So improve the event detection accuracy and efficiency given a limited number of waveform data. And then, okay, with this information that we gather from the detections, we would like to delineate what are the fractures and failures that are associated with those microseismic data. Okay, so here's the Illinois Base Project, which is the U.S. Department of Energy project, which successfully injected 1 million ton of CO2 onto the subsurface by the end of the year 2014. So there is much interest into this site. It's a relatively new project, and this extensively integrated site. Characterization and modeling investigations are necessary. So here. And using microseismic data, we aim to improve the detection of low magnitude unified event, unidentified events, and locations to discover undetected and hidden faults in the fracture. So this is what the site would look like. These are the monitoring wells from the site, and we are currently looking at the bottommost sensors, which are the PS32 sensors, PS3 sensors, here, and they would be the closest sensors to the injection site, which is down here, really far down in the Mount Sinai. Okay. And we are specifically here looking at a time period where there is a lot of activity occurring from Micro's activity during the injection, compared to the rest of the injection period. Okay, so you can see there's higher activity, and then it reduces down to be more stable. So we call this high activity period the active period, obviously, and then we did call the subsequent period the transition period. And all these are relevant to cluster number 2 event in the catalog. So it is a very highly active fault plane in the site. These are the fault plane imagings in those sites. So we are currently looking at cluster number 2, and then we will talk about cluster number 4 as part of the analysis here. So the cluster number 2 actually only occurs to 612 located events in that time, which is a very small number for training our models. So now we're going to talk to our models. So currently in our model, we're using 3-channel data. And then like I mentioned, we only have 612 events. We are here showing how these data differ from an actual event in time and then the noise. And then with this data will be used as inputs to our model, but we found it more efficient to actually use the spectrograms of the models, the spectrograms of the samples into our models compared to not. And then to increase our data size, we not only use the 612 events from a single sensor. These are 3-channel events from a single sensor. We use 2 of the bottommost PS3 2 sensors to increase our data set. So 612 2 times 2, 1,200 events. And yeah, these events also are a very slow magnitude. So the range of the magnitude of these events are between -2 and 1. So relatively lower than most seismic events. And then it's not enough to simply set the inputs of these data sets to our model. So what we did was to use, we bandpass filtered all of the data, and then we transformed them to waveform spectrograms, but then we rescaled the spectrograms into a log transformation, which help us reduce or change the distribution of the data as you see here. So this helps normalize the data better for our models to be able to learn better. And then we took all the data and we split them into training, validation, and testing. So we use 70%, 20%, 10% respectively for all the data. And this is what our data looks like, what our models look like. Okay, so we use the input data, we rescale spectrograms into log transformation as the base model, which right here, the CNN block, which I will call the base model at the moment. Then we also tested using the MFCC or parallel MLP model using MFCC features, which are actually information taken from another. It's used for MSCC are a representation of short-term power spectrums and sounds as perceived by the human hearing. So in terms of sound processing, it's a Fourier transform presented in a Mel scale, logarithmic scale, and subjected to preset Mel filters. We use, the default is 20 filters, but we also applied for a reduced model. And then for architecture, is kept as a simple CNN model so that it's has less training parameters so that it is good and small for small training data. And the MSCC inputs can be added as physical constraints to help the model do better predictions. The best model saved is based on the best validation losses on the data and trained model applications. We then, after getting the best validation model, we tested on a 1 second moving window on continuous data to gather more events for the catalog. Then here we're showing how much detection does our model do on our base model. We can see that it tends to pick more events than the actual triggering system of the IBDP site, and it tends to detect even more during the transition periods, and we're going to show you quickly soon why. At this point, we also trained our FaceNet model, which was part of the next phase of this project, and we give it a very strict gave it a very high percentage on how to pick. So that's why it picks. But both our models are both saying that there is much more events in the site to be looking at than that are reported on the catalog. So here we can see the detections during the active periods and the transition periods. The active periods detection have more similarities to our actual training data, where you can see clear PNS arrivals between 0.68 and 0.69, but there is also a few other events that are not very similar, but that is good. I mean, our model is able to detect between the base-like noises and the actual data. But what happens during the transitions period? And the transition periods, which is a little more quiet period, I noticed a lot of detections having been continuous or subsequent windows. So I expanded the view on the windows, and I found these events happening, which are a much larger type window that would be detected with our modeling. But it is interesting enough that these events were captured by our model, but they were not captured with the triggering system. So yeah, they are represented as low shear slips on hydraulic fracturing, and they observed in the literature where natural fractures and high density are likely caused by high poor pressure and high clay content. Let me try to move faster. Then for our modeling, we can see clearly that rescaling the spectrograms dramatically improves the model accuracy compared to base machine learning models. And then using the MFCCs even further improves the model in time. As you can see, a lot of the MFCC models still are lowering their losses, so they are constantly still learning, and they have high capabilities of learning more. And our model is left so our model is so much smaller than most that it is very easy and super fast to train compared to other models. And yeah, let me try to finish already. Okay. Rescale spectrograms as input. Properly normalizing the data as input dramatically improves the ML accuracy. Simple CNN models trained on clear data are able to efficiently detect and induce microseismic events. And CNNs are able to detect long period, long duration, which is events which are not capable, which were not detected with the standard triggering system of the site. And during the transition period, seismic events tend to be long and overlap, and PS32 sensor tends to be higher in amplitude. And presenting additional data-driven inputs to the model, and then in a different format, and to make improve model data classification. Oh God, thank you. Sorry.
All right. Thank you, Daniel, for the wonderful presentation. And those of you who are in the audience, it's time for you to type in any questions if you have one. In the meantime, I have very basic question. I'm not an expert in this field, but I imagine in the world there are places of different geology and tectonic activities. Do you see your model can be applied
Yes,
fairly easily to other systems?
the model is kept very simple precisely for that very capability of implementing them in other sites very easily and very timely. And we, in this project, are currently getting data from another site, so we will be applying this to it. And yes, it should be easily applicable to other projects.
Okay.
I have a
Please.
question if there's
Oh, yeah.
I have kind of like two questions. My first one is, how much is noise affecting your training data set? Like, is it something that has really frustrated you throughout your project? And my second question is slightly related, but it's like, does your machine learning model detect events that aren't subsurface events? So, for example, if you're recording like trucks coming in on the day and things like that, is that something that you've noticed?
The noise data. Even though these are low magnitude events, they are very noticeable characteristics. It's not been much of a problem, and then for our machine learner is able to detect various type of waveforms, which, and to the second question, could be something else happening during the moderating. Okay, and then it is not like, it has been a question whether what type of events are related to what type of the data that we're getting, right? So it could be something like a truck, like you mentioned, but that is where the second phase, which we're not showing here, comes into. The phase net model is the one to tell whether these events have seismic characteristics or not, right? So our model only detects what it detects, and it is very data driven. So most it is, you know, informed of what is a seismic event or not.
Okay, we have one more question from the audience. So Taimur Hassan has asked, how much is the magnitudes can be categorized as a microseismic event?
How much? Uh, so I don't calculate the microseismic magnitude of the event. I'm taking that from known catalog information, and then as long as the activity appears to be a seismic event, and with the characteristics of having the initial P arrivals or the secondary S phase arrivals, you can be categorized as a microseismic event.
Is there a minimum magnitude that you have as like your cutoff?
So the magnitudes that I gave are from the catalog, as I mentioned, and they have determined that it is from -2 and 1. I do not calculate it, and I do not discard any data that is either above or beyond it. It is still data that should be checked or more a study. So that's why this model sends it forward to the other models so that we can characterize them and give more descriptive stuff about the site.
Okay. We have another question from Mohammed. What is the window size of your data fed to the model?
We're using 2-second window size, which were 2K hertz data. That would be what is it, 4,000 data points? Yeah. So we're using for this model, we're using the 2-second data window, but for the subsequent ones, we are reducing the window to be more focused onto the event. So once we detected the window, we reduce the window size to better characterize the event.
Okay. And we have another question from Timur. Is your machine learning microseismic event detection model available on GitHub?
No, these models, which this is just the first one out of 4, are currently part of the SMART project, and they are currently in development. And maybe they will be available, but not at the moment.
I see. Thank you. I don't think we have more questions, but thank you again, Daniel, for your wonderful presentation. Oh, we have last minute question from Mohammed. I think this will be the last question. So it is, what if the model sampling rate was not 2K? Do you resample it to 2000 before applying the model?
So that question seems to be how I set the model. So I can set the model to any model parameters, right? I can use less or more data in the window, but at the moment it just seemed to be reasonable to use a 2000 data window based on the catalog events because not that precise. But we can make the model to any window size, right? If you want to resample the data, yes, you can, but that would not be my recommendation. Or my recommendation would be to structure the machine learning model based on your data. So I would go higher or lower on those sampling.
All right. Thank you, Daniel, for the presentation. And if you have more questions to Daniel, you can leave comments in the YouTube video that will be posted or send him an email. So I think we can now conclude our session today. So next up in May, we have another 2 speakers who will be presenting. So it will be right before the Interpol begins. So it will be a nice prelude to the Porous Media research if we are planning to join the Interpol 2025. So please stay tuned for our advertisement for this session. And these sessions are brought to you by Interpol and Interpol Young Academy. And here are the members of the Interpol Young Academy, which are composed of early career scientists, researchers around the world. And also you are part of this. So if you like to present your research to us, or if you have someone who are interested in speaking in our session, please send us an email shown at this slides. And yeah, we'll conclude this session, and I hope you guys see you next month. Take care.
You.